Go through to the AR4, look at the main sections in those reports on what the key evidential information is for comparing with climate change. Now, when we talk about climate change and look for evidence and what it is that's causing temperature change in particular, we have to rely on temperature data from a lot of different sources. Today we have lots of instrumental stations making measurements continuously over large parts of the globe, but of course that wasn't always the case. So to extend further back in time, particularly over the period when human colonization started to impact the environment, we have to look at so-called proxy data, particularly over the last 10,000 years or so. And particularly going back, say, a couple of thousand years, we tend to look at things like tree rings, the number and density of those, which are a good indicator of response of plant life, trees in particular, to temperature change. We also look at the growth rates, etc., in coral reefs, which are a good indicator of water temperature. Most corals are fairly close to the surface, so that's a relatively good indicator of surface air temperature. And then, of course, we've got ice core data, which are the main proxies, and we've got historical records as well, because even they can be quite useful for validating some of these data sets. So a lot of those records typically stretch back about 1,000 years. Some go back a couple of thousand years, but of course the uncertainties get larger and larger, and they don't typically cover the globe. It's mainly the northern hemisphere that they cover. Now, most of those proxy data are not actually temperature measurements. They have to be compared, normalized against current temperature data, so that we have some idea about how these different proxies respond to changing air temperature. And effectively, some of those are shown there. It doesn't matter which are which, but you can see there's quite a lot of scatter in some of those temperature data, but the trends are more or less the same, despite the very different sources of those data. For example, they all tend to show the Little Ice Age and the Middle Ages quite well, and they all tend to show this slight warming period, so-called medieval warm period, which occurred from about 950 to about 1250 AD. So we can get some confidence from those reconstructed temperatures. So I guess the question is, well, how well do the modern instrumental measurements compare to previous measurements? Well, for CO2, it's actually quite good because we rely on ice core data. And what this shows is the merged record from ice core data. This one is actually from the Law Dome in Antarctica. And the closed black circles show the trended arithmetic average of air measurements of carbon dioxide from Mauna Loa and the South Pole from instrument measurements going forward from about 1958. And these open black circles here are from the Law Dome, and they overlap quite well, as you can see. So again, we have confidence not just in temperature, but also the links to CO2 concentrations in the air as well. And we have reliable data, quite high resolution data, going back to about 1740, and even further, of course, as we showed earlier. So we tend to rely on these temperature data an awful lot to essentially estimate the impacts and what the reasons for global warming are. And we typically see measurements from the industrial period through to the modern day, as shown there, presented as usually 5-year annual means compared to annual means to look at the spikes and the natural variability. And for example, we can use periods. These particular annual means are typically based on difference, anomalies compared to the period 1961 to 1990, for example. And we can use those to compare with current global measurements and look at the global temperature differences on a year-by-year basis. And what you can see is that typically most areas of the globe have started to warm. This one is for 2007. But the warming, of course, is particularly noticeable in the northern hemisphere for reasons we discussed previously. So if we were to look at a typical trace of global temperature from about 1850 up to 2010, say, these are the sorts of comparisons to give us confidence in what those temperature trends look like. And we never rely on just one data set. What you can see here are data sets compiled by 3 independent research groups. So the one in black is from the Hadley Centre at the UK Met Office Climate Research Unit. The one in red is from the NOAA National Climate Data Centre, and the one in blue from the NASA Goddard Institute for Space Studies, or GISS. And you can see that they all agree pretty well, but there are differences between them. What are those differences? Well, some researchers, some data sets try to extrapolate data where there's very few data points. The further back in time you go, the fewer measurement stations there are. And that's particularly true of regions like the Arctic and Antarctic. So what do you do there? Well, some people have algorithms which they've developed to interpolate temperatures in sparsely covered regions of the globe. Other people don't do that at all. For example, the Met Office Hadley Centre simply says that if there are no data within a certain distance of each other, certain stations, then they won't do anything. They'll simply leave that information out of the data set. So the Hadley Centre Hadley Centre data set, which is shown in black there, that actually is typically constrained between plus 60 degrees north and 60 degrees south. So those are the latitude bands that they look at. So that's the black line. Whereas the GISS, the one in blue there, they will infer and try and estimate what the temperature is at latitudes beyond plus or minus 60. And you can see that there are differences, but by and large they agree extremely well. The same for the NOAA data set as well. The grey line shows a very detailed analysis of the uncertainties based on all the measurement limitations. So effectively, these are the error bars, and what those tell us is that essentially that the global temperature at a particular year will fall within that grey bar, grey area, grey shaded area, in 19 out of 20 cases. So the 95 percentile, if you like. So we have a lot of confidence in the temperature going back, certainly over the last century. As you can see, the error bars get larger as we go back beyond that. So that's the information we need to look at and start to think about what the impacts are. And if you look carefully at that data set, you can see some quite interesting things. For example, most of the observed increase has occurred in the mid-20th century onwards. And we know that that's likely based on the increase in anthropogenic greenhouse gas concentrations, emissions from fossil fuel use mainly. There's more uncertainty in the earlier part of the 20th century, and we also have to bear in mind that there are influences that we discussed on temperature globally, such as solar variation, volcanic emissions, and uncertainties in the early days of what the actual emissions of carbon dioxide were from human factors. And of course we also have to think a little bit about the natural variability that's internal to the climate system, and we discussed that when we looked at ENSO, for example. For example, you can see quite a few warm spikes on these traces. For example, there was a very strong El Nino in the 1870s. Remember, we used the Tahiti Darwin Index to identify when that might have occurred. There's also one in 1998. And of course, we also get big dips as well. We get these so-called cold spikes due to La Nina, and they occurred between 1990 to 2000, and there was another strong one in 2008. We also have to remember that some of those dips are caused by volcanic eruptions, which can lead to a global cooling. For example, Mount Agung in 1963, Mount Pinatubo, 1991. Oops, sorry. And why have we picked those two particular volcanoes? Well, they were particularly large, but they were also in the tropics. And remember our discussion about the Hadley cell circulation, which are very good at transporting air from the tropics to the polar regions. Well, we have a volcanic eruption, and it's a big one, in the tropical region. Of course, that will facilitate transport of aerosols on very large scales, leading to more impact in terms of global temperature, in this case cooling. So tropical volcanic eruptions are particularly important. Once we have some confidence in the temperature, of course, we can start to compare the global average temperature to other factors which we know should respond to temperature. The two obvious ones, for example, would be the global average sea level. How is that going to change as we increase temperature? Well, it's a little bit more complicated than just warm water expands, although that's a large factor. And of course, we can also start to look at the northern hemisphere snow cover. So, for example, the second chart down here shows the global average sea level rise, and again, this is the difference in millilitres compared to the average from 1961 to 1990, so it's the sea level anomaly, if you like. So that's mainly based on tide gauge data, because we have a much longer record using tide gauges. But more recently, we also have that red line data set, which comes from satellites, because now we have these continuous satellite measurements which can measure globally sea level very, very accurately. And you can see that they overlap very well, albeit over a relatively short period so far. And of course, we can also look at northern hemisphere snow cover. Now, the trend is not quite as clear, but certainly over the last half century, we're beginning now to see a decline in northern snow cover. We'll talk a bit more about those in a minute. So remember, all these changes are typically relative to 1961 to 1990. Those smooth curves on there are actually the 10-year running means, or the decadal average values, to try and smooth out some of the decadal oscillations. The white circles show the yearly values. That's typically the way you present this information. And the blue area are the uncertainty intervals. And again, that's based on a comprehensive analysis of all the known uncertainties in the measurements. So, we also have, of course, other temperature measurements from the atmosphere, not just surface temperature measurements. We've got balloon-borne and, more recently, satellite measurements, which give us measurements in the mid to lower troposphere, as well as some in the stratosphere. And indeed, most of the trends we see in the mid to lower troposphere are also quite consistent with the surface temperature trends. There were a lot of issues that were highlighted in the third assessment report, basically showing that there were some significant differences between these measurement data sets, and that was eventually tracked down to errors in radiosonde measurements, those balloons that measure temperature, humidity, pressure, etc., but also some issues with satellite measurements as well, because satellite measurements are not perfect. They have to be validated with in situ measurements. But most of those issues are now sorted out. And based on that, we can also say that the average water vapor content within the troposphere has increased since at least the 1980s, both over land and over the ocean, but also in the upper troposphere. And if you warm the air, of course, you can hold more water vapor. And the increase in the amount of water vapor is consistent with the extra water vapor that this warmer air could hold. We have measurements since 1961 that show that the average temperature of the global ocean has increased to depths of at least 3,000 meters. The ocean has been absorbing more than 80% of the heat added to the climate system. There's some debate over that, and that figure will change. And of course, such warming is going to cause the seawater to expand, and that's going to contribute to sea level rise. And we'll look again in more detail at that in a minute. Now, if we do compare the surface and satellite measurements, this is what's done in this graph. Again, this is the temperature anomaly, and the blue line shows the surface temperature measurements, and the red and green show measurements from two different satellites of what they think the surface temperature is, but also the temperature in the lower troposphere, which is consistent with the surface temperature measurements. And you can see that the trends are more or less similar. So we have confidence both in the satellites and the surface measurements are seeing the same thing. And of course, these measurements are continuously updated. What we see here in black are the global temperature measurements based on the surface measurements or instrumentation, compared to the balloon measurements or radiosonde measurements, as well. The dotted lines show the respective trends. So the surface measurements are in black. The red shows the lower troposphere measurements measured by the balloons. Of course, they give measurements all the way through the troposphere. And again, you can see that the trends are quite similar, although the warming seems to be a little bit higher in the mid-troposphere. Now, the advantage of balloons is that they provide, these radiosonde measurements, is they provide in situ measurements. The advantage of satellites is that they provide global continuous measurements. But the problem with satellites, remember, is that they're not actually homogeneous, because satellite orbits decay. One has to essentially correct for instrument decay with time. One has to correct for decay of the orbit, and also for orbital drift. And of course, because they're not actually completely continuous, because as the satellites decay and the instruments fail, they have to be replaced by another satellite. So you have to have some overlap between a new satellite and the old satellite. So the biggest uncertainties in satellite data are mainly those periods where they're trying to overlap the satellites to compare different instruments. So that's quite a lot of work goes into that. Now, while balloon measurements are not as continuous, they might be once a day or once every few days, depending upon the region of the globe, they do go back much further in time. And as I mentioned, there were significant differences between the radiosonde work and the satellite measurements, but those have now been resolved, particularly in the fourth assessment report. And effectively, what we can now do is use a whole range of these satellite measurements to compare with surface measurements. And you can see that certainly from 1960s onwards, they tend to agree pretty well. There are differences. The grey is, again, a data set put together by the Hadley Met Office, and the other red-green measurements are from satellites, and the blue line is from another, is from the NOAA surface data sets, based on surface measurements. Now, if we have a look at the trends in there, you can see typically about a trend of about 0.131 degrees centigrade per decade for the so-called RSS satellite. That's the one in red. Whereas if we look at another satellite, the so-called MSU or UAH satellite, that's again got a trend of about 0.138 degrees C per decade. So very similar. Over on the right here, you can see the trends as calculated for different periods. So 1979 to 2011 in this report, and 1938 to 2011, so even further back in time. And what you can see from these different dots is that the trends seem to be increasing over those two periods. And of course, we also have to keep in mind much more detailed information in terms of ENSO, using these so-called multivariate ENSO indexes today, which have more or less replaced the old Tahiti-Darwin index we talked about. So, we continue to compare temperature trends between all these different data sets to give us confidence. We said that satellite records have the advantage of continuous global coverage. It's not fully homogeneous for reasons we talked about in terms of instrumentation and orbital decay and drift. We did see some large differences between the reconstructed temperature series at certain times, because there's poor overlap between successive satellites. That makes intercalibration difficult, but that's more or less been resolved now. Balloon radiosonde record, not continuous or global, but it is much longer. There have been complaints, as we mentioned, of data problems with both satellite and balloon measurements, but those have now all been resolved due to large scientific meetings which have got to the bottom of a lot of these issues. So we can have more confidence today about those data sets. So if we look at just a basic summary of what we're seeing in the temperature trends, we see that surface temperatures on average show about a 0.07 degrees C per decade over the past century, and about 0.17 degrees C per decade since 1979, and that's increasing slightly now. Temperature trends in the lower troposphere up to 2012, end of 2012, show, based on the different data sets we just showed, satellites about 0.131 degrees C per decade to 0.138 degrees C per decade. So those are the trends in the lower troposphere compared to the surface measurements. Again, we keep updating every year the globally average combined land and ocean surface temperatures. They're normally, the trends are normally calculated using a linear regression, and they show a warming of about 0.85 degrees C between 1880 to 2012, say, when this report was written, and that's using multiple independent data sets. The total increase between 1850 to 1900 and 2003 to 2012 has gone from 0.78 degrees, ranging from 0.72 to 0.85 degrees C. That's the increase in the average temperature. Now, if we look at the longest period when we have a very complete data set, that's about 1901 to, in this report, 2012, almost the entire globe has experienced surface warming, as we showed in that contour plot. Okay. This is a reference to the scientific working groups, numbers 1, 2, and 3, and you can find some summaries in the fourth assessment report of those working groups of the IPCC. And I would suggest you look at topic 2, which looks at the causes of the observed changes in temperature globally. So have a look at that report, you can download it. And we'll just very briefly go through some of those points that they highlight. The first one, of course, is sea level rise. So what causes sea level rise? Well, it's not just expansion of water, we have to think about melting of snow and ice. We know that mountain glaciers and snow cover have declined on average in both hemispheres now. There's wide decrease in glaciers and ice caps, and those contribute also to sea level rise. Now, when we talk about ice caps, be careful. In a climate sense, ice caps do not include contributions from Greenland and Antarctic ice sheets. Those are actually treated separately. Okay. In the third assessment report, data that was new then showed that losses from the ice sheets in Greenland and Antarctica had very likely, in their words, contributed to sea level rise between about 1993 to 2003. So the data set there showed it was very, very likely that those losses, based on calculations of the additional water volume provided by those melts, had actually increased sea level. Also, we can measure the flow speed from these glaciers, and certainly the flow speed from Greenland and Antarctic glaciers has increased. And of course, those dray ice from the interior of the ice sheets, and that increased ice sheet mass loss is then followed by ice sheet thinning, or you get a reduction in the so-called ice shelves, or loss of floating glacier tongues in mountainous regions. And this dynamical loss is sufficient to explain most of the loss of ice mass in Antarctica, and at least half, now more, based on recent analyses, of the ice mass loss in Greenland. So, global sea level rise, what has that been doing? Well, typically it's been rising at about 1.8 millimeters per year between 1961 to 2003. That rate is increasing. Now, whether that rate reflects decadal variability or an increase in the actual long-term trend is still being debated, but the evidence suggests that there is high confidence that that trend is due to sea level rise due to warming and ice melt. And in fact, the total 20th century sea level rise is around about 0.17 meters. Doesn't sound like much, but remember that's a global average. Sea level rise is not the same depending upon where you are. It can vary significantly. Now again, for that period, 1993 to 2003, if you look at the sum of the climate contributions contributing to sea level rise, they're all consistent within their uncertainties with the observed sea level rise. And this is how they break down the sources of sea level rise. Typically, you look at two different periods, 61 to 2003, 93 to 2003. And you can see that, of course, warming of water expands, so thermal expansion accounts for most of the increase. These numbers are in millimetres per year. Glaciers and ice caps come next, so again, 0.5 millimetres per year from that. And then, of course, we have these two additional ice sources, treated separately, Greenland and Antarctic. They're not quite as large, but still significant. And if we look at the sum of all the individual climate contributions to sea level rise, we got about 1.1 millimetres per year over that period. Quite a large uncertainty there. But the observed sea level rise was 1.8 millimetres, so there's quite a big difference between that. But of course, as we get better, the data gets better, if we look at this period here, you can see that the comparison between the sum of all those terms and the observed sea level rise is actually much closer. So we're getting more confidence year on year, that this sea level rise is due to thermal expansion and glacier and ice cap melt. So you'll notice typically over that decade, 93 to 2003, we were looking at of the order of 3 millimetres per year, which has increased from the previous decade. So we continue to monitor sea level rise, and typically you will see graphs like this. So this is again the sea level change in millimetres from 1870 up to about 2015, and most of the data still relies on tide gauge data because that's the longest record we have. But of course now, since about the 1960s onwards, particularly the 1980s onwards, we have satellite data, and that gives us much more global coverage. And you'll notice that the rate of change based on the more recent data is actually around about 3.4 millimetres per year. So again, consistent with that previous table we saw. In fact, the measurements in the end of 2015 suggested that the change was about 76 millimetres in total since 1993. Okay, snow cover and ice extent. Well, again, satellite data show that there are very likely, again in the words of the IPCC, to have been a decrease of about 10% in the extent of snow cover since 1960s. So that affects, of course, where you're going to go skiing for your holidays, but it's actually also important for a whole range of environmental issues and also supplying water to various communities. Ground-based observations show that there is likely to have been a reduction of about 2 weeks in the annual duration of lake and river ice cover, both in the mid and high latitudes during the late 20th century. There's been a widespread retreat of glaciers in mountains in non-polar regions during the 20th century. And in the northern hemisphere spring and summer, the sea ice extent has decreased by at least 10 to 15% since the 1950s, and that's increasing. And it's likely that there's been about a 40% decline in Arctic sea ice thickness during the late summer and early autumn over the last few decades, and there's a slower decline in winter sea ice thickness, although that has been more of a worry based on new measurements recently. So in the next 20 years, some people say there'll be a summer route through the Northwest Passage, which links the US eastern seaboard with Japan and Korea by the seaway north of Canada. There's a lot of debate about when that passage will appear. Some people say it might be 2030, some people say it might be 2050. We'll look at a couple of graphs in a moment to see what you think. So, we rely quite a lot now on satellites to look at the ice extent, and in particular we look at the periods when we have, particularly in September in the Northern Hemisphere, we look at the period when there is minimum sea ice coverage. And there are definitions for that based on there has to be at least 50% coverage to be able to say there is ice there. So this shows a comparison between 1979 at the top and 2003. Now you might look at that and say, well, it's hard to see a big difference, but if you look carefully you can start to see some of the passages opening up. But more interestingly, if we look at the latest data, which was published last year, this again is based on the NASA SSMI data set based on satellite measurements. And this is going to show you the minimum, or I beg your pardon, the yearly minimum ice coverage period. And there's going to be a graph which is going to show you the minimum value as we progress with time. So just watch this for a second. I'm assuming it's going to work. So we start out at around about 7 million square kilometres. This, remember, is the area coverage, not the volume or mass. This is the area coverage. And you can see there's quite significant annual variation, but we can see a general declining trend as we go forward to the decade between 2010 and 2020. Now you'll notice between about 2010 and 2012 there was a lot of concern because of this very large change, where we're basically down to more than half of the sea ice area had essentially vanished. And people were panicking a little bit, and then of course it increased again. But that again is part of the decadal natural variability which people are still trying to include in models. So sea ice cover is actually quite complex, and including it in climate models is one of the challenges currently. But as we'll see, those models are getting better. Now that continued reduction in the area covered by summer sea ice is a very dramatic presentation of the pronounced impact of increased global temperature, particularly in the Arctic region and the Northern Hemisphere. What's more concerning is that there's also been a significant reduction now in terms of the amount of older, thicker sea ice. So come winter, the remaining ice will then start to thicken and grow again. But it looks like the thickness of the winter sea ice is actually not as thick as it used to be. So it's becoming much thinner, and that means come the summertime period it will tend to break apart and disappear much more rapidly and won't be there to essentially reinforce the sea ice coverage the following winter. Now most of this information in terms of the area coverage is based on microwave data coming from satellites, and most of the data we know has been very good going back to around about 1979. There is some data prior to that, but the good data is from 1979 onwards. So those are the most relevant and I think impactful data that show the impact of global warming on sea ice coverage, particularly in the Northern Hemisphere. Similar issues occur in the Antarctic, although the trends are not quite as clear there. It's much more difficult because of the huge area covered by ice. But again, there have been increased breakup of the ice shelves. For example, this one here in the Antarctic Peninsula region. If you look at the top right picture, that shows this enormous breakup of the sea ice shelf there off the continent. And this little black box there is zoomed in here. And one of the things you can see are all these melt ponds. So those become more prevalent and larger, and those melt ponds can then enhance fracturing of the ice shelf, and that will lead to even further breakup. And of course, that can then precede an enhanced breakup the following summer. Now, while the trends are less clear, we do seem to be seeing a lot more of these breakups, as you can see in that photograph there. Now, as we said, satellites normally track the area of ice, but of course they can't give us the ice thickness. And to do that, we have to rely actually on submarines. So actually, there have been a lot of submarines making measurements inadvertently under the Arctic using sonar. These are, of course, military submarines, but the data sets are available. And since 1971, those data sets have been used to actually measure the ice thickness. So this shows the volume of the ice based on those measurements. The units are not particularly important, but you'll see that the ice thickness has declined significantly. So again, this is the ice thickness at the minimum part of the year, and effectively what people are trying to do is apply a trend to that data set and see when effectively the ice thickness disappears completely. That might be an indicator, for example, of when we might see the entire passage that we talked about becoming clear of ice, particularly in the summertime. Now, as we said, this data set only went out to about 2010. As we know, there's been a slight recovery here. So some people were arguing that we were going to get an ice-free passage by 2015, but other people are arguing that it's more likely to be about 2030 when we see a consistent ice-free passage. And we know that the thickness of the ice has declined very, very significantly. As you can see, we've gone down from about 15 on this scale to around about 4 by 2015 or later. So that's a very large fraction of the ice mass has been lost. So again, if we look at the mean sea ice anomaly, again this is based on the ice area extent. This is the monthly mean from the Northern Hemisphere again. If we look from January 1953 through to December 79, again that's from the Hadley Met Office Centre, you can see this fairly constant value, but then over the last few decades you can start to see this significant decline, which is essentially accelerating. So, remember, the thinning of the ice is caused by a mixture of reduced growth in winter of the older ice, because the warmer temperatures and more heat from the underlying water column and greater melt in summer essentially reduce that ice thickness. We get a change in the direction and speed of ice motion as well, which we haven't really talked about here, and that also plays a role, particularly within the Arctic basin from what's called the Fram Strait, rather than recirculating many times inside the Arctic, contributing to further ice build-up, so that is weakening. And then we have the summer area of sea ice, the minimum, that reached a record low in 2007, almost matched in 2011. It then recovered a little bit in 2013, but now it's starting to continue to decline. It is inevitable, based on all models and all predictions, that very soon there'll be a downward collapse of the summer sea ice levels. It is inevitable based on current understanding. Now in 2007, measurements indicated that during summer there are about 2 meters of ice melt from the bottom of ice flows into the Beaufort Sea, while in the neighbouring first year flows they'd only reached a depth of about 1.8 meters during winter. In other words, all the first year ice was disappearing. So it wasn't available for the following year to build up the ice. So that effect is going to become much more important and will spread throughout the Arctic basin. Now, how do the models compare with the observations? Well, again, this shows the sea level extent. It's in millions of square kilometres. So we start out in the observations at just over 8. The red line in the observations there. The models. And there's a lot of different models, as you can see. The average of all the models is shown in the black line, and the dashed black line shows the standard deviations of all those models. And of course, one of the concerns was that in this decade here, particularly the decade 2000 to 2010, you'll notice that the observations were actually showing much more rapid ice loss than the models. So people had to go back to the models and figure out what they were missing in the models. We can't discuss all the details here, but you notice some models actually did predict the ice extent correctly, and most of the models are now including the components in that model that weren't included in their own models. But of course we have to be very careful, because that could be just a blip, and as we saw there was some recovery in the following year, but of course it's going downwards again. And you'll notice these models tended to indicate that on average, sea ice would essentially stay until the end of the century. Most of the models now say it's going to be 2050. So those are the old models, and they're currently being updated to try and take into account the actual observations. So the end of summer extent of Arctic is reducing far more rapidly than those so-called alarmist IPCC models predicted. That was a concern, so scientists have to fix the models. Okay, what other evidence do we have? Precipitation. Put more water vapor into the air because of evaporation of the ocean surface or lakes and seawater and river water, etc. That's going to effectively transport more water vapor, and eventually, of course, what goes up must come down, and we're going to get more precipitation. And in fact, precipitation has increased by between 0.5% and 1% per decade over the 20th century, and that's over most of the high and mid latitudes in the northern hemisphere. Rainfall has increased by 0.2 to 0.3% per decade over the tropical land masses as well. In the mid and high latitudes of the northern hemisphere, over the latter half of the 20th century, there's been between a 2 and 4% increase in the frequency of heavy precipitation events. So the frequency of these very heavy precipitation events, due to the transport of receptor water vapor we mentioned, has caused big increases in the heavy precipitation events. And of course that can lead to more floods. And of course those have resulted from changes in the atmospheric moisture, as we mentioned, and that also leads, of course, to more thunderstorm activity, much more large-scale storm activity. More water vapor is essentially a way of putting more energy into the atmosphere. Since 1950, there's been a reduction in the frequency of extreme low temperatures, so we don't tend to see those very much. Of course, a couple of weeks ago in Manchester you did. And we have a smaller increase in the frequency of extreme high temperatures. Now, this was written in 2013, and of course the increase in frequency of extreme high temperatures has been increasing. And just as a typical example of what impacts that can have on local populations, this shows the glacier and ice cover, etc., and snow cover around the Cotopaxi volcano in Ecuador. It's one of the largest in that region, 5.9 kilometers above sea level. So this satellite picture was taken in 1986. This one in 2007, at the same time of year. And based on those, we can estimate that the ice mass has decreased by 30% between 56 and 76, and then a further 38% between 76 and 2006. And that is closely tied to the temperatures that have been changing in that region. Why is that important? Well, a lot of the cities, particularly the capital city of Quito, essentially rely on the ice melt from these glaciers to essentially provide water supplies. And of course that's going to impact a lot of the communities in that area if those water supplies are going to decline at that rate over the next few decades. We can also look at glacier melt. So these are some historical photographs on the left. The one on the left is of the Bear Glacier in Alaska in July 1909. And you can just about see in the middle of that picture the glacier tongue as it's spreading away from the mountain region. If you look at the same region in August 2005, effectively it's completely gone. We have a forest there now. If we look at the bottom left, that's the India Glacier in the Himalayas, showing the glacier melt in autumn of 1956. And if you look very carefully at the picture on the right, you can effectively see a complete collapse of the lower tongue of the glacier in the background and the formation of these very large melt ponds instead of frozen lakes. So that's quite common now. So, just over the last 5 minutes, let's just summarize some of the evidence for climate change and look at the changes. So these are now categorized in the following table in most of the IPCC reports. Essentially, you look at the phenomena and you look at the trends as best you can based on the data. So, for example, you would look at warmer and fewer cold days and nights over the land areas. You then look at the warmer and more frequent hot days and nights over land areas. You then look at warm spells or heat waves and the frequency of increases over land areas. You'd look at, as we mentioned, heavy precipitation events, their frequency, or the proportion of total rainfall from heavy falls, and whether or not those have increased over most areas. You then look at the areas that might be affected by droughts and whether or not those drought frequencies have increased. You then look at the intensity of storms, tropical cyclone activity. You then look at the increased incidence of extreme high sea level, not including tsunamis, which are a different phenomena. And if you look at all of those over different periods, you can see that typically in the late 20th century, the change has all been very likely or likely. If we look at the likelihood of human contribution to the observed trend based on climate models and analysis of those trends, then again it's likely, or more likely than not. Remember, this was in 2013 this was written. And then the likelihood of future trends based on various projections, which we'll talk more of in the final part of the course where we look at energy production. So we're looking at the likelihood of future trends based on projections for 21st century using these so-called SRES scenarios. And again, we'll talk about those special report on emission scenarios later, but have a look at that if you want to. And again, they say that essentially those phenomena and the changes and the predictions from those changes are virtually certain to occur and or very likely or likely. Let's check the time here. 1 minute to go. Okay. I think, yeah, we'll continue with this tomorrow. Just to say that the evidence continues to strengthen. Climate records continue to be broken, as I'm sure you're aware from watching the news. There are a few updates to those graphs, which you can find on Blackboard in the news update section. For example, 2016 was the warmest year on record since 1880, depending upon which data set you look at. Average global temperature across land and ocean surfaces for 2016 was about 0.94 degrees C, in excess of the 20th century average. Global average of 13.9 degrees C. And that surpassed the previous record maximum in 2015 by 0.04 degrees C. And the global temperature in 2016 were mainly influenced by strong El Nino conditions, so we've got to be a little bit careful, that prevailed at the beginning of that year. But of course, since 2016, those records are beginning to be broken again. So we'll continue tomorrow by looking at radiative forcing estimates. So thank you very much for coming.
Thank you.